So let's discuss about the number of elements in a given set. We begin by considering a universal set U. Now, inside this universal set, we're going to consider a set A. Now, because we are interested in finding out the number of elements in a given set, so here we will suppose that A is a finite set. That means there are countable number of elements within the set A. Now, for the set A, the total number of elements is given by, so here we're going to use a notation. We'll use little n, and within parentheses we're going to write A. So this means that we are considering all the elements of the set A. Here there's a requirement that A has to be a finite set. Only then this particular notation makes sense. Okay, now we're going to consider another set B. Also, set B is going to be finite set. The other set B, so B is overlapping with A. We'll come back to that in a moment. So for the finite set B, the total number of elements will be n of B. Okay. Now, once we are familiar with the idea, so let's take a quick example. So let's say if we have A given by A, B, C, and D, and we have the set B given by 1, 2, and the set A. Here, the number of elements in the set A, that's going to be equals to 4. So here we're 1, 2, 3, 4. It's a countable set with 4 elements. And for B, the number of elements in the set B, that's going to be equals to, we have one element, that's 1, the second element is 2, and the third element is the set A. So that means there are 3 elements here. We don't have to count the elements of the set A, we have to count the set A, which is as an element of B. Okay, so there are 3 elements of set B. Now the question is, if we take the union between the two sets A and B, what will be the total number of elements? Then we can ask the question, if we take only the intersection between A and B, what will be the total number of elements? If we are interested in calculating only the elements in A but not B, or elements in B but not A, then what will be the total number of elements present in each of the case? So let's try to understand them one by one. So here we have two overlapping sets A and B. Let's say we take the union between the two sets A and B. Now, we can also represent A union B as the set containing only the elements of A. So that's going to be A minus B. Then we're going to take its union with the set containing elements from both A and B. So that's going to be A intersection B. And then we will take its union with the remaining elements of the set B that contains only elements from B, not from A. So that's going to be B minus A. B minus A. Right, let's label this as number 1. Now, using this, we need to find out the total number of elements, in the intersection between the set A and B. Okay, so how do we do that? Now, first, let's try to use this and expand it. Now, we have A union B equals to one set, that's A minus B, union with another set A intersection B, union with the third set B minus A. Now, if we take the total number of elements on both sides. So if we take the total number of elements of A union B, that's simply going to be equals to the total number of elements in A minus B. Then we're going to add it with the total number of elements in the common region A intersection B, and then we're going to add it with the total number of elements in the region B minus A. Now we're going to label this as number 2. Our goal will be to define a total number of elements in A minus B and the total number of elements in B minus A. So let's do that. So what we say, the total number of elements in A minus B, from the Venn diagram, it's clear that we're considering all the elements of the set A, and from here we are subtracting the elements that are common to A and B. So from the Venn diagram, this is quite evident. So let's going to label this as number 3. And when we discuss about the total number of elements in B minus A, that's simply taking the elements in B and from here subtracting the elements common to A and B. Fine. So let's call it number 4. So now that we have the total number of elements in A minus B as well as in B minus A, we're going to substitute 3 and 4 back in equation number 2. 2. So that means now in equation number 2, we have the total number of elements in the set A union B. So this will be equals to total number of elements in A minus B. Now that's simply defined as total number of elements in A minus the total number of elements in A intersection B. Added to, now we have total number of elements in A intersection B. So let's keep it as it is. Total number of elements in A intersection B. Added to the total number of elements in B minus A. So that's going to be number of elements in B minus the number of elements in A intersection B. Now, as we can see here, the total number of elements in A intersection B, that's repeating. So what we'll do, we will subtract one of them, and this is going to be simply equals to the total number of elements in A added to total number of elements in B minus the total number of elements in A intersection B. So this is how we can calculate the total number of elements in A union B. Now, if we don't want to go through this particular route, there's a simple way to just remember how the particular formula came to be. So here, we consider all the elements in the set A. Right. So that's the in A union B. We're considering all the elements in the set A. And then we're going to add it with all the elements in the set B. So we have to consider all the elements of the set B, including the ones that are common with A as well. So this is going to be the total number of elements in set B. Now when we took all the elements in the set A as well as added with all the elements in set B, you can clearly see here that we counted the elements that's common to both A and B twice. We need to only count it once. So all we have to do is subtract the common elements between A and B because it was counted twice. So this is how we can easily remember the total number of elements in A union B. Fine. Now this particular formula holds true when we assume that A and B has got some common elements. What if A intersection B equals the null set? This simply tells us that the two sets A and B are two disjoint sets. Right? So that means they are not going to be overlapping with each other. That's the meaning of two disjoint sets. Now what that means, there is no common element between A and B. So if there is no common element between A and B, this simply means this implies that the total number of elements in A intersection B, so that's going to be 0. Now if this is 0, then our formula is now going to be, our new formula is going to be N of A union B. That means the total number of elements in A union B, that's simply going to be the sum of the elements in A added with the sum of elements in B. So N of A intersection B is going to be 0. So this only holds true if the two sets are disjoint. That means there is no common element between both of the two sets. Now we can extend this idea to 3 sets as well. So that means if we have 3 sets A, B and C and we take the union between these 3 sets, that's simply going to be equals to the total number of elements in A union B union C will be simply the sum of the elements in the individual sets. So we have N of A plus N of B plus N of C. Or we can generalize it. So let's say we have the sets A's of I. So where I goes from 1 to n. So we have, let's say, n number of sets and we're taking the union of each of the sets and we find out the total number of elements on each of the sets. Then this is simply going to be equals to the sum of the number of sets in the individual AI, where I goes from 1 to n. The index might create a confusion later on, so let me change it. It runs from 1 to m. Similarly, the summation goes from I equals to 1 to m. So here n is simply talking about the total number of elements in each of the given set. What if A, B and C are not disjoint? If they are not disjoint, and our goal will be to find out the total number of elements in the set A union B union C. The total elements in A union B union C, that's now going to be, we'll consider all the elements of the set A added with all the elements of set B, and we also added to all the elements of the set C. Now, however, when we're adding all the elements of set A, B and C, we observe here that we are counting this intersection between A and B twice. So that means we need to subtract the elements A intersection B because we counted it twice. While we're taking the elements of set A, we consider this elements in this region. This is A intersection B. Let's note it down. This region is A intersection B. While taking B union C, we also consider this particular region. We count it. We have A into this is B intersection with the set C, and this region will be A intersection the set C. So here, what we'll do, we are going to subtract the total number of elements in B union C, and we're going to subtract the number of elements in A intersection C. Fine. Now, while taking the union between the set A and B, we have this region A intersection B, but there is also this particular region which is a portion of A intersection B. So when we removed A intersection B, so this particular region got removed once. Then when we took B union C, then we have the intersecting region B intersection C, but we subtracted B intersection C. That also removed this particular region once more. So that means 2 times it got removed. And finally, when we removed A intersection C, then this particular region also got removed once. So that means it got removed 3 times. Although it was counted 3 times, it got again removed 3 times. Then what we'll have to do, we'll have to compensate for it by adding that particular region. So that region is nothing but the intersection between all the 3 sets A, B, and C. So we need to add to it. Okay, so now this is clear. We will understand it with the help of few examples later on. But next we will discuss what if we take A union B and we take the complement of A as well as the complement of the set B, and I ask the question, what is the total number of elements in this particular set? How do we approach about it? So here we'll be using an idiom. Since all the sets A, B, any sets we consider, it's always going to be a subset of a bigger set, that is the universal set. So here we know A complement union with B complement. This can be also expressed. We're going to use the De Morgan's law. We take A and B because we are taking the complement, and then this union is going to become simply the intersection. So we take A intersection B, and taking its complement gives us A complement union B complement. Now that we have A intersection B and its entire complement, this can be also expressed as what we do. We have the universal set, and from here we are subtracting the set A intersection B. So that's only going to leave us the complement of A intersection B. That is the definition. So now when we take the total number of elements of A complement union with B complement, this is simply the same as saying take the total number of elements in the universal set, and from here subtract the total number of elements in A intersection B. So that's going to give us A complement union B complement. Similarly, we can also define for A complement intersection B complement. So that's going to be what? So that's going to be A union B using the De Morgan's law. We have A union B and its complement, and simply the universal set minus A union B, which means that the total number of elements in A complement intersection B complement, that's going to be the total number of elements in the universal set minus the total number of elements in A union B. Fine. And we can find out A union B. We already have the standard formula. That's n of A plus n of B minus n of A intersection the set B. Let's try to understand how to calculate the total number of elements when it is present in exactly 2 sets of the 3 sets A, B, and C. This could be best understood with the help of a Venn diagram. So here we are considering 3 overlapping sets A, B, and C. Now let us suppose that an element belongs exactly to 2 sets at a time. So that means it could belong to A intersection B. So our elements could belong to A intersection B, or it could belong to the intersection between the set B and C. So it could belong to B intersection C, or it could belong to the intersection between A and C, intersection between A and C. Right? So this is the way how we can make sure that the elements can belong to any of the 2 sets. Now, because it's not mentioned which particular two sets it is, so we have to consider all the three possibilities. It could be A or B, A and B, it could be B and C, or it could be A and C. But we need to be a little bit careful here. When we are considering elements that belong exactly to A and B, now this is the region that contains exactly A and B, but we also have one region which is going to contain some elements from the set C. Now that means we will have to subtract these common region which also belongs elements from set C, and this region is nothing but A intersection B intersection C. Now that means from, if we are taking A intersection B, then we will have to exclude the elements A intersection B intersection C. So this is going to be the one of the set. Or if we are taking the common elements between B and C, that means we are assuming the elements is exactly present between B and C, then we have to exclude A intersection B intersection C as well. So that means we will take B intersection C minus A intersection B intersection C. Or the third scenario would be we take A intersection C only and we subtract A intersection B intersection C. So these are the three possibilities. Now that means the total number of elements belonging to exactly two sets at a time. That means we will take the total number of elements in A intersection B, but we'll have to subtract the elements that's common to A and B and C as well. So we'll subtract A intersection B intersection C from it. Then we will take the elements that belongs to only B and C, but we have calculated an extra portion that's A intersection B intersection C. We'll need to subtract it. A intersection B intersection C. And then we have the total number of elements in A intersection C, but we'll need to subtract the total number of elements A intersection B intersection C. Now if we combine them, then we get the final result. So we take the total number of elements in A intersection B, add it with total number of elements in B intersection C, added to the total number of elements in C intersection A, minus the, now here this number is repeating 3 times, so we have 3 times the total number of elements present in A intersection B intersection C. So this is the formula that we will be using when we are interested in finding out the total number of elements present in exactly 2 of the sets. So what if we want to calculate the total number of elements present in exactly only one of the set at a time for 3 sets A, B and C? So here we again have 3 sets A, B and C overlapping with each other. So we only want to calculate exactly in one of the set. Okay, let's begin by first considering that the element is present in set A only. So we will consider all the elements in the set A. However, since we need exactly in the set A, we do not need any other contribution from the set B or set C. Now here we can see we have the total element set A, so we'll have to exclude this particular portion. We have to exclude this particular region, and we'll also have to exclude these regions. So that means there are 3 regions that we need to exclude out of A, so to get elements present in the set A only. Okay, so what we'll do, we'll try to subtract all the extra elements from here. Now let's begin with this particular region. What is this region? This region is actually, if we consider the entire region, this is the total number of elements present in the set A intersection B. However, we are only concerned about this region. Let me use a different diagram here. So this is the region that we're interested in. So here we need to subtract this common region. So this is the intersection between all the 3 sets. So we will be subtracting the total number of elements in A intersection B intersection C. So this is going to give us this particular region as well. Fine. So this is A intersection B minus A intersection B intersection C. Okay, fine. Next, we need to take only this particular region. So this is the region which is, let's keep it aside. We're going to add it to the total number of elements in A intersection B intersection C. Fine. And then finally, we're going to consider this region. So this is the region which is the total number of elements. Now this is a region common between set A and set C. We have set A intersection with set C, but here we also have this extra region. We need to get rid of it. So we are going to subtract A intersection B intersection C. Fine. Now, when we combine all of these 3, then they were going to get a total number of elements in A minus we have total number of elements in A intersection B added with the total number of elements in A intersection C. We have one of the total number of elements in A intersection B intersection C cancelling out, leaving us with only a single A intersection B intersection C. Fine. Now, let's open up the brackets. So we have elements in the set A minus elements in the set A intersection B minus elements in the set A intersection C plus elements in the set A intersection B intersection C. Fine. So this is going to be number 1. So let's consider it to be the elements present in only the set A. Similarly, we can define the elements present only in B. So that's going to be number of elements in the set B. And from there, we're going to subtract the number of elements common to B intersection C and the elements common to A intersection B, added to the total number of elements in A intersection B intersection C. This is number 2. So this is only going to be present in the set B. And finally, we have the elements present in only C. So that's going to be total number of elements in C, but we need to subtract from it the elements common to B and C, as well as the elements common with A and C. But we need to add the total number of elements A intersection B intersection C. So this is the element present in the set C only. Now, when we add all these three, that's going to give us, because this is it could be present in A only, or it could be present in B only, or it could be present in C only. So we have to consider all of these 3 cases. So when we combine them, we're going to get the elements present in the set A added with the elements present in the set B added to the elements present in the set C. Now here we'll see that the total number of elements in A intersection B, and so that's going to be repeating twice. So we have 2 times the number of elements in A intersection B. Similarly, we'll see that the elements in A intersection C, that's also going to repeat twice, and then we have 2 times the elements in B intersection C, and we add all these 3, then we are going to get plus 3. That's multiplied to the total number of elements in A intersection B intersection C. So this is how we can calculate the total number of elements present in exactly one set only. So here I have listed out all the formulas that we discussed today, and the last 2 formulas number 6 and 7, these are 2 very specific keys of number 3. So this will be used in solving few numerical problems. Okay, so let's end the lecture here today.